because of the variability that we just discussed. Because for analog, you need to have a very precise result. The error keep accumulating. And then after they develop for 10 years or something, the digital computer picked up, right? Because they become smaller and faster, and eventually they just replace analog computing. That's why nowadays you don't study analog computing. However, it is still very important, right? So let me give you 1 minute, right? Just in your brain or have a paper. Draw an operational amplifier. Ask yourself how many input it has, how many output it has. What's the relationship between input and output? And what is an ideal operational amplifier? Okay, so I will draw it in this way, right? It has two inputs. One is called V in plus, another is called V in minus, but you can call it anything. And then it has an output. This is the typical one, right? It can have other version, but I will just draw it this way, right? It has two inputs and one output. And what is the relationship between them? It is the output equals to, it must be related to the two inputs, right? Otherwise, it's useless. So as someone say, it is A 0 times V in plus minus V in minus, right? So it's differential. It get an output, not just depending on V in plus, not just depending on V in minus. It depends on the difference between them, right? For example, if this is 10 and this is 2, this is 1, I get 10 as the output, right? If this is 3, this is 2, I also get 10 as the output. What it cares about is the difference of the input. That's what it amplifies, right? What is an ideal operational amplifier? First, what is the input impedance? Do you remember? Infinity, right? When I look into here, I will say very huge input impedance. So no current is flowing into there, okay? I must be 0 for ideal one, okay? What is the output impedance? 0, right? We will discuss, review a little bit more later why we want it to be 0 when it is ideal, right? So it means when I look into here, the output impedance has to be 0, okay? Now, besides this, what else? We want it to run very fast. Okay, so the bandwidth needs to be infinity, yes, right? I have a amplifier that has very good gain at 0 Hertz at DC. Basically, useless for me because it needs to respond to some fast signal, right? High frequency. I want it to work even at 1 gigahertz, 10 gigahertz, right? Another thing you will learn later is so-called the slew rate. It has a little bit relationship to the bandwidth, but they are not the same. It's saying that how fast you can respond to the input. It still gives the correct results, but you say, hold on, wait for 1 millisecond, then it will bring you to the right result. We also want this one to be infinity, okay? Per second, the outputs can go up by very fast. Another thing that we have been assuming, but sometimes we are not aware of, is the range, the swing, or the output swing is infinity. It's saying that the V out can be any value. For example, 10 volt, 100 volt, 1000 volt, right? But in reality, it is limited by what? The supply, the VDD and VSS, right? So you need to think about this. What else do we have? Biasing. We assume the biasing is given. Yeah. One more thing is the gain. Okay. Now this one is a little bit tricky. Sometimes we say we want the gain equal to infinity, but sometimes we just say give a finite gain, the rest still satisfied, we still treat it as ideal. It doesn't matter. This is just a definition. It's not really a definition, right? So you will see that some people have different definition or different thought in their mind. So when you go to word better, talk to the other clearly. What do you mean by ideal amplifier when you start discussing, right? Otherwise, after you argue for the whole day, you find that, oh, I was defining A0 equal to infinity, but you are defining that it is finite. Okay, but be aware of this. And why? Because later our goal when we design the amplifier, we want to have infinite input impedance, zero output impedance, very wide bandwidth, very large slew rate, very good swing, and then very high gain. Okay, you won't be able to achieve it because we cannot. Nothing is ideal, but that is our goal. Okay. So we just said that. So let's look at this circuit. This is what you just drawn, the operational amplifier. I have 2 input and 2 output. Although I call it V in 1, V in 2, doesn't matter, right? And indeed, my equation here should be changed to V in 1 minus V in 2. Because the V in 1 is connected to the plus, and V in 2 is connected to the minus. Is this okay? And then I can draw an equivalent circuit as this one. Why I can do that? You see that what the circuit do? You say that I take an input to the plus terminal, V in 2 to the minus terminal, and I don't care how it works. It's a black box for me. I will then produce a voltage at another side, which is equal to A0 times V in 1 minus V in 2 as the output. So this actually doing what I want, right? Because what is the input impedance if I look into this? Can I have any current goes in? No, right? Because this is open circuit. So indeed, I have Z in equal to infinity. It matches what we want. How about the output impedance? Again, very good, just the wire. Some of you may be confused. How about this voltage source? So we will discuss later, but if just trust me, when you measure the output impedance, you need to ground, by definition, ground the input impedance. So this is going to be 0, just a wire, okay? 0 output impedance. How about the bandwidth? Anything tell me that it has a limited bandwidth? If this one has a very high frequency, this equation, just do it accordingly. Doesn't change. A0 is there. No capacitor is drawn here, right? Bandwidth is infinity. Don't see capacitor, you still don't know slew rate well, so just trust me. No capacitor, infinite slew rate. I can bring up the voltage in no time, okay? And the swing, no limitation also in this model, because whatever you put in, I just give you whatever. You put 1 trillion, my output is 1 trillion times A0, yeah? So this one does represent the you can say a model for this amplifier, right? But we are very often we just use this one, which is okay. But in your mind, that you also know that this one is representing this one, right? So this is a review of the operational amplifier. Okay. Well, I will move a little bit faster, but you have a real question. You have a big question. Just let me know. We can discuss, right? Otherwise, I will go through and then come back again, as I said, right, and do the second time. Now, so with this, then I can start playing with my operational amplifier. This is the one what we have. What can I do? Well, the first thing is, what if I grant the input? So here we know that V out equals to A0 times V plus minus V minus, right? Sometimes when we do the equation, all you need to do, just be careful. Write down everything. Carefully map clearly to the circuit. This equation can be from my cheat sheet. No problem. I know it is correct. Then I start mapping. What is V plus in this case? V in 1, right? Even you don't understand, it is not wrong. You know you are correct. What is V minus? 0, right? Very straightforward. So you see that the output related to input is positive. Now, you may say, well, isn't that you say you have 2 input for operational amplifier? But it depends on how you use it, right? You are the user. You maybe just want to supply 1 voltage. Fine. Then you decided to grant it. For you, this whole system is just amplifying your signal. Although in reality, it's trying to find the difference between these 2 signals. But because you grant it, right? The whole overall effect is that it is only amplifying your signal. V in 1 times A0 give you V out. And we call this a non-inverting configuration, right? Because if you have a positive value, it gives you a positive output. It has a gain. So similarly, I can do the same thing by grounding the plus terminal, right? So I repeat what I wrote earlier. This is just from the cheat sheet. And then I say V plus is 0 because I ground it. And V minus is my input now, right? Although I call it input 2, you can call it anything V in, right? So this is negative A0 times V in 2. So it inverts my input, right? So it is an inverting amplifier. So an operational amplifier is very useful. If you bias it correctly, it can invert your signal or just go to the same direction, which you already know, right? Just a review. Okay? Nothing special. So let's review one more time about this ideal operational amplifier. We have this equation, right? I also say that we have infinite input impedance, 0 output impedance, infinite response speed, which is the slew rate that we discussed earlier. Infinite bandwidth, infinite swing, not limited by VDD, VSS. But there's one thing we have been using very often in other class. Virtual short. Do you remember this? When very often we say that V plus equal to V minus. But is this true? Is this always true? Here I tell you that no. It only happens if you have infinite gain, which you are okay, you know that. But we always forgot one very important thing. It need to be, the transistor need to operate under normal condition, which is saturation, and you need to have a feedback. So let me ask you, if I have an operational amplifier, I just give you, which has an infinite gain, right? I pass you the chip. The gain is infinity. Is this terminal equals to terminal? This terminal. Are these 2 terminals, do they have the same voltage for these 2 terminals? This is infinity. The gain is infinity. Do they have the same voltage?
There's no feedback, so no.
There's no feedback, there's no, right? There's nothing to tell them to be the same, because I can easily show you that no, because I buy a AA battery, I connect it to 1.5 volts, and then I buy another AA, another 2, I connect it to 3 volts. They are not the same, right? It is infinity, right? So this is my input. I have the freedom to do anything. The reason I can say this is because if I have a correct negative feedback, for example, this is my V in, and then I do something, whatever, right? This is a simple one. I have this feedback. Then it will force this one to be the same when the gain is infinity. This is the only case you can say I have a virtual short, right? They are not short to each other, but they have the same potential. That's called virtual short, right? Make sense? So I hope you trust this. But now, how about in this class? Whenever I give you a circuit with feedback, you can take it for granted, I mean, at least in the exam, that you can use this equation. But when you are a circuit designer, you are the one who designed the circuit. You cannot assume they are virtual short. You cannot say that I already short, yes, it must be virtual short. Or it must be operating under a normal operating condition. It might not. You need to check, right? Later, when we talk about feedback, you know how to check it, right? If it is not, then all your equation will be wrong if you assume that they are virtual short. Right? This is very important. So if you don't trust yourself, should you trust your colleague? No, right? They say that I designed this, just analyze it. I designed it very well. And if you find that it does not work as what you think, you better check the assumption. The gain, is it large enough to assume it is infinity? The second, is it really working well with this negative feedback? If not, you cannot assume they have the same voltage. Okay, so this we can discuss more, but now I just want to tell you, what is the meaning of inserting an op-amp in your circuit? Well, of course, it has some function. But what it does mathematically, it just gives you an extra equation. Because I insert something new, right? You better give me another equation. Otherwise, I cannot solve the circuit. So you give another set of equation on top of KCL and KVL, right? You know what is KCL? The current law. If I have node, right? Then I have, for this node, right? I have some resistor or whatever coming in. This is I1, I2, I3. It helped me to get one equation. We say I1 plus I2 plus I3 has to be equal to 0, right? How about KVL? Well, just any system, for example, this one, right? If this is V1, this is V2, right? Then, of course, I know that V1 plus V2, right? I better use the potential drop instead. That will be easier to illustrate. I say this is V1. The potential drop is V1. From here to here is V2. And from here to here is V3. For example, I can choose the convention. Then I set V1 plus V2 equals to V3, right? That gives you another equation. How about the op-amp? Now you have two choices. If the gain is finite, which equation do we have? What equation we just said? The one on the top. V out equals to A0 times exactly V plus minus V minus. Is that okay? right? And you're very fast. If A is infinite, then which one do we use? V plus equals to V minus. Okay, but can we use this all the time? You need to check if they do have the right connection, right? If not, then you will use this one, because when they don't have the right gain or whatever, this one the gain might not be infinity anymore, right? But just for the class, for the exercise, you can use this. But when you start working, always challenge yourself, okay? What is the meaning of infinity in EE? Is it really infinity? No, right? There's no infinity. Say again? Very large. But what is very large? $100 million to me is very large. But for Bill Gates, he even doesn't want to think about it, right? So it needs to be compared to something, right? Compared to the rest. For example, you say a resistor is very large. Fine. You say, okay, because all other resistors only about 10 ohm, 100 ohm in this path, but this path is almost 1 mega ohm. When I do my equation, I can treat infinity. But if the rest are actually 1 giga ohm, you better treat this as a short. So same for infinity and ground and zero, right? So if you play with these two numbers well, it simplifies your life a lot. But if you do it wrong, everything will be wrong. Okay. So after this, we actually can start doing something difficult. This is a unity gain amplifier, the simplest amplifier we can have. We look at it carefully, I see that the gain is 1000. And the input is here, the output is here, right? The first question is, well, I have a circuit, I can use KCL, KVL, but because of op-amp, I better have an op-amp equation, right? Otherwise, I cannot solve it. Which equation should I use? Should I use should I use V out equals to A0 times V plus minus V minus, or V plus equals to V minus? I have two equations. Remember what we said here? If it is finite, we use this. When it's infinite, we use the other one, right? What do we have? Finite. So we should use the top one because it is finite, right? So we pick our equation, right? So we start working with this. VO is just V out. That is exactly what I want. My goal is to find again the relationship between V out and V in. A0 is given, fine. What is V plus? Just V in, yes, right? And what is V minus? Oh, yes. You actually implicitly use the KVL, right? Because these two nodes are connected together in some sense, right? So this is V out. Then we try to see, this is a simple one. We try to check, well, yeah, in this equation, do I have more unknown? No, right? Because V out and V in, we want to keep it. A0 is given. So the rest are just math. So that's how you solve the equation. Think about what you need to put and then get rid of the variable. The rest are just math, right? And in my class, if you can get to the final stage without solving, you probably get 90% already in the midterm. Because I'm not testing your algebra. You can use Mathematica, right, to do that. So then I will start playing with this. But if you set up the wrong equation, then I will deduct more points, right? I just expand it and then move the V out to the left, right? This is 1 plus A0 equals to A0 V in. And then by definition, this is very important. The definition, the gain is V out over V in, which is equals to A0 divided by 1 plus A0. Okay? That is what it is here, right? Okay, good. What is this value? Why it is called unity gain buffer? If this is not equal to 1,
but it equals 0.999.
good. when it is equal to 0.999. Thank you. Yeah. So when A naught is very large, when the A naught is large, A naught divided by 1 plus A naught is just almost equal to A naught divided by A naught, because 1 plus something very large is that thing, right? 1 plus 1,000, about 1,000. 1 plus 1 trillion, about 1 trillion. That's why this is called unity gain buffer. So in ideal case, infinite, if it's infinite, then your V in will be equal to V out. It's a buffer. Now, you may say, what is the point of having an amplifier with a gain equal to 1? The important thing is that it is a buffer. Later we will learn that, because this can help you to transform the output impedance to be a small one if your first stage has a large output impedance. I get the same gain, but now I also have a good output impedance. It's a buffer, right? So we can study that later. Do you see virtual short in this case? Almost, right? Because V out equals to A0 divided by 1 plus A0 times V in. And we just say that this is almost equal to 1, the gain. So V out almost equal to V in. So maybe this is not a good way. Then, but V out is what? V plus, and this is V minus. So V plus almost equal to V minus, right? That is a virtual short. Okay, move faster. Okay, so this is the summary. I won't go over it. It's just what I have said, right? Now let me challenge you, right? Give you also 1 minute. You won't be able to finish, but I just want you to think about how you are going to solve this problem. I have another inverter, and you do say that I have a feedback, and you trust me, this has a proper feedback. And this time I assume A0 is infinity, right? What is the gain of this circuit, right? You won't be able to solve. Just think about the strategy, right? And then we will try this together. Again, you won't be able to finish. Just think about the strategy. So maybe we can start asking ourselves which equation to use, right? We have two equations. So one is this one, V out equal to A0 times the difference of the inputs. Another is V plus equal to V minus. So which one should we use for this given condition? Right, because it is infinity, right? So we assume there is virtual short. Because you trust me, the feedback is good, okay? But you need to check it later, right? If it is your product. So we say V plus equals to V minus. And because of this, I don't know what I'm talking about. Assume A0 is infinity. What is the gain? Oh, the gain, I'm talking about the overall gain. Right? So which equation should we use? We will use V plus equals to V minus, which give us V in 1 equal to V in 2. This is one equation, okay? Now, which is good. But however, now we have this problem. Yeah, you have V out equal to, V in 1 equal to V in 2, which means this is also equal to V in. Right. So basically, I'm saying that this is V in. Because of the virtual short, this is V in. So this is also V in. Right. So I'm almost there. Then what is the relationship between V in and V out? Okay, some of you already memorized the equation of voltage divider, but let's just take a look again. But you do need to know how to use this one, right? You don't want to waste time to derive it, right? But this time I derive for you one time, right? Look at this circuit. V out, R1, R2, and then this V in. Okay? Now, I'm going to use KCL. I1, I2, I3. What is the relationship between I1, I2, and I3? Well, isn't that it is I1 equals to I3 plus I2. Am I right? No, not even need to think about KCL. I don't know why. Of course, he got the name because they derive a more rigorous and physical way. Right? Otherwise, this is a common sense even for a baby. When your river, your water flow on this river, it need to add up. It need to be the same as those it branch to the left and those it go forward. Right? That's a common sense. Intuition, not common sense, right? So I1 equal to I2 plus I3. What is I3?
0.
Why? Yeah. So that's why the definition is very important. Why we spend so much time keep saying it is infinite output input impedance. Because this is infinite input impedance. Yeah. So the current is going to be 0 if you have, right? And because of this, I have I1 equals to I2. And then I start with the Ohm's law. V0 minus V out minus V in divided by R1 equals to V in minus 0 divided by R2. Do you see this? Yeah. And this then brings us to the KCL and the potential divider. I won't. You just solve it. I won't spend the time on this. You will get V in, right, which is this node divided by V out equals to R2 divided by R1 plus R2. Is it the same as what you remember? Yeah, that's how you get this, right? So try to derive one more time if you forgot. But then in the future, you understand that when I have this potential divider, this one is equal to R2 divided by R1 plus R2. But you can use this only because you know no current is going to this direction. If there's current going in this direction, no, you cannot use this equation. You need to do KCL, KVL one more time. Right? So remember what are the assumptions that you are making, right? So with this, then now I know that, this is the gain already, right? Then from here, then I get V out divided by V in equals to R1 plus R2 divided by R2, which is 0, 1 plus R1 divided by R2. Is this okay? That is the gain. And that's it, right? The process is very simple, right? You see that if I'm very familiar with the potential divider effect, I can already say that this is V in through the virtual short, and then this V in and we already have this effect. Not much equation, right? But you need to approach it correctly. Okay? So this is the same thing I just showed you, the non-inverting amplifier. I just redraw it. Why it is non-inverting? Because the gain is positive and because the input goes to the positive terminal. And this is the equation we just derived, right? So you see the virtual short concept is very important. If you know that you can use virtual short, it saves you a lot of time. Now, sometimes I also want you to practice this, right? Not just for EE, but for your daily life also. When you go to extreme case, it can help you to verify some theory. We just say that the gain of a non-inverting amplifier is this. Now, let's try to say, what if L2 becomes infinity? It means it becomes very large, right? So you build a non-inverting amplifier, it works. I take away this resistor, make it infinity, or put in a very huge resistance. What should be the value? Let's look at this equation. When R2 becomes infinity, right? V out divided by V in equal to 1 plus R1 divided by R2. When R2 becomes infinity, what is this? 1, right? Does that make sense? Now you look at this circuit. When R2 becomes infinity, this is open. Have you seen this circuit before? What is that?
Unity gain buffer.
Unity gain buffer. But isn't that unity gain buffer does not have R1?
So it's just like any resistance.
There is a good argument that maybe that's why resistance. However, in our derivation, we assume there's no resistance, right? Can you think a little bit more? Why this is still a unity gain buffer? Or why the derivation is going to be the same as before? When, yeah, see? No other path. When will a resistor be important in a circuit? The reason a resistor has effect is because you have current going through it. Then it causes potential drop. If there's no current, there's no difference between having a resistor or not, right? Do we have a current going through here? Exactly. Because of the infinite input impedance. There's no current, right? So V out still equal to V in minus. Then all the derivation we did before is still valid. So this is just a buffer. Unity gain buffer, right? So this is they are consistent. Makes sense. Yeah? From the circuit topology, it become a buffer, so I expect the gain is 1. From the equation you derive, R2 becomes infinity, it is also 1, everything match, right? So try to see in this way. What if R2 becomes 0? What will be the gain? Well, what's the gain? Based on this equation? Exactly, equal to 1 plus infinity equal to infinity. Oh, so you are saying that if this become grounded, then the gain is infinity. Now, look at this circuit. Does it make sense? Think about that. Does it make sense? When I have infinite A0. Now, I basically saying this is grounded. And I say the gain is infinity. Make sense? Yeah, because now it just becomes open. How to say? No feedback, right? Suddenly don't know the word. Open loop. Yeah. It just becomes this op amp. right? And isn't that we already know that V0 equal V in times the gain, and your gain is infinity. Yeah, the gain is infinity, right? This is the new topology. Make sense? Yeah. Okay. So this is a good way to check your answer. Now another thing to check your answer in the exam is to check the unit. I asked you for the gain. What is the gain of the voltage gain? What is that? What is the unit? Voltage divided by voltage. Unitness, right? And if you came up with an expression has R0 or GM, then you know you are wrong. But if you get GM R0, you know you might be right because it's unitness. Ohm times 1 over ohm, right? So try to have this practice, okay? Okay, good. Now then, I want to talk about the same amplifier, but this time, I'm not going to give you something easy. We are going to do finite A0, right? So this involves a lot of math, but there are some skill we need to learn. So can I use virtual short now? It has feedback, but the gain is not infinite, right? So I cannot do that. So what I need to do is to use this equation. V out equals to A0 times V plus minus V minus. Okay, so this is my first equation. Well, of course, I know that then I have two variables, V plus V and V minus, that I don't want, right? So the first equation is, I know that V plus equals to V in. This is an easy equation, trivial. Another equation that I know is V minus is equal to the potential divider effect, right? Again, it's exactly the same as this one. V minus, right? Although the gain is not infinity, but the input impedance is still infinity, right? So I still know that this must be equal to this, right? Still have the potential divider effect. So I can use that equation, V minus equals to V out times R2 divided by R2 plus R1. Right? See slide, which slide? 15. Right? We have this equation already. Okay? Then I just combine them together because this eliminates all the issue I have. Then combine them, I have V out equals to A0 times V plus, which is V in, minus V minus, which is V out, times R2 divided by R1 plus R2. So I'm basically done. I have the right equation. The rest is just math. Okay? So I will try to move V out to the left. Then I get V out times 1 plus A0 R2 divided by R1 plus R2 equals to A0 V in, right? I move this term to the left, right? So this is 1 plus A0 times the whole thing, right? And then I get something very bulky. The gain is V out divided by V in, which is equals to A0 divided by 1 plus A0 R2 divided by R1 plus R2. I got the answer already. Yeah, question?
I was going to say, wouldn't it be easier to interpret the equation to multiply the whole thing through 5
Yeah. Later. I got the answer already, yeah? But he's not happy. He said as an engineer, but just getting this thing, it means that you don't know engineering because you don't have insight. Can you arrange the equation so we can recognize it and know what it is? Particularly, we already have the ideal case. Now, when the gain is infinity, I have 1 plus R1 divided by R2. Now, when it is not infinity, can you arrange the equation so that I can see how it is different from the ideal case, right? And that is what makes you variable, right? Do you see what I mean? So let's do the same thing, right? This is the answer already, but I'm going to rearrange it. My goal is to factor out this 1 plus R1 divided by R2. So what I can do is just multiply the numerator and denominator by R1 plus R2 divided by R2. So I get A0 times 1 plus R1 divided by R2, right? Because this one is just R1 divided by 1 plus R2, so it's going to cancel the bottom one when we multiply this to the bottom also. Then I get 1 plus R1 divided by R2 plus A0. Are you okay with this? Right? This one is R1 divided by 1 plus R2, R1 plus R2, right? This whole thing. So what I'm doing is multiply the top with this, then I'm okay. Then I multiply the bottom with this 1 will get this. And then this A0, because this R2 divided by R1 plus R2 will cancel with 1 plus R1 divided by R2, right? So I get A0, okay? And I will do one more simplification, right? Because now I get this 1 plus R1 divided by R2 out. I have the form that I know from my ideal case, the infinite gain, right? How about this one? Because I know the math, and you will know that after, right? Or I read the textbook, right? This is, I am going to divide it by 1 over A0. Then isn't that this becomes this? Right? So what I'm doing is I just take this term out. Numerator divided by A0 becomes 1. Denominator divided by A0, so this becomes 1. And this becomes 1 over A0 of the whole thing. Okay. Now I need to emphasize A0 usually is large. So this term is small. Think about A0 is 1,000, 10,000, right? Then this is very small compared to 1. Then based on what you learn in Taylor expansion, right? You just trust me, we don't need this in this class, right? Taylor series. We know that 1 over x plus 1 is approximately equal to 1 minus x when x is much smaller than 1. Okay, you trust me. But that makes sense, right? 1 over 1 plus 0.001 is approximately equal to 1 minus 001, right? Because 1 over 1.001 is approximately equal to 0.999, right? You can try it with your calculator. So because of this, now I came up with the final solution. This one equals to 1 plus R1 divided by R2. The whole thing becomes 1 minus this term, which is 1 plus R1 divided by R2 divided by A0. And that is what I have here. Now, I know this is too much math. You don't worry if you cannot follow now, right? You just go back. I'm sure you can follow. It's messy. But the main point in this slide is that when we do the finite A0, we use this equation. And then we just use KCL, KVL, potential divider, whatever you know, to group get rid of this V plus and V minus that we don't want. And then eventually we group them as V0 divided by V in. And that is just math, not important. The important thing is now I want to transform this one so it is similar to my ideal case. I again use some math technique, multiplication, and then the Taylor series. Again, you can go back to study. And I don't expect you to do this in the exam, okay? But you need to know that. At least you know that you can Google. By doing this, I'm able to transform this complicated equation to something that can give me insight. That is, when the gain is infinity, it is 1 plus R1 divided by R2. When the gain is not, it is 1 plus R1 divided by R2, the same, but what times 1 minus something. If this thing is 0, then I have the same result, right? When it is 0 is what? A0 equal to infinity, right? When A0 equal to infinity, this is 0, right? So this is like an error. The error, not really an error, it's just compared to my ideal case. And that is what we call the gain error, right? So again, you compare these two equations at this extra term. And the gain error is because of this. This is in percentage, right? You can say, you can make it into percentage. And what does it mean? It's just like that. Ideally, I want to make a non-inverting amplifier with gain of 10, which is this one. But because my open loop gain is not infinity, the gain I get may be only 9.99. So I have a gain error of 0.1%. Okay, so this line is tell you the skew. You will do that for the inverting amplifier in the assignment. But more importantly is that, what's still so many? Okay. Yeah, is that you still, more important is to understand the skew, okay? Okay, now then let's look at the inverting amplifier. This one is much easier. Now what I want you to do is, I assume the gain is infinity. So which equation should I use? Now you should be very familiar with this, right? Thank you. V plus equal to V minus. And then we use KCL and KVL. Let's use KCL. This is I2. Let me call this I2. And let me call this I1, right? So by KCL, what do I know? I2 equals to I1, right? Hey, how about the current going to here? 0. Thank you. Because we assume it is ideal, right? So whenever you do something, you need to ask yourself, is this correct? Okay? So I2, just Ohm's law. V in minus Vx divided by R2 equals to Vx minus V out divided by R1. You need to be very careful when you use Ohm's law, right? You must know where is the initial voltage, where is the terminal voltage, and then divided by the resistor is the current flow. Do not do V out divided by Vx. If you want to do that, fine. Then you need to define I1 as going in. And then when I1 is going in, you will find that now it becomes I2 equal to negative I1. Okay, be careful of this. But we say that Vx is just V plus, right? Which is just V minus, right? And what is V minus in this case? 0. So it's not just virtual short, it's also virtual ground, right? They are shorted together, fine. But not just shorted because this is ground, so I'm also virtual ground. Then you solve the equation. You get V in divided by R2 equals to negative V out divided by R1 because I do the right thing, right? Then you get this relationship. So you have a negative gain. So it's an inverting amplifier. Okay, so this is relatively simple. Now with that, you can ask yourself the same question. How about it is finite, the gain, right? So I'm not going to show it here. You will do it in your assignment. But basically is decide which equation to use and then use KCL, KVL, and the Taylor expansion. And then you will get it, okay? Okay, so that's all I have today. Any questions? Yeah. You can come here to ask.